Next Monday. Next Wednesday. 今天是 Wednesday 吗？对啊 ，Wednesday. Yeah, yeah, yeah. 19 minutes. 19 minutes. Me turn. And 在哪呢？ Oh, okay. Last time we finished talk about CSTR in series, right? So the last slide we talked about last time is at slide 32. Okay, so now please go to slide 33. 33. Let's talk about PFR in series. The scheme for PFR in series. Suppose there are two PFR connected in series. Okay. So for the molar flow rate, at the beginning, the molar flow rate is FA0. Passing through the first reactor, the molar flow rate at a certain point, like 0.1, the molar flow rate is FA1, right? Passing the second reactor, like here, the 0.2, molar flow rate is FA2. Also, after passing the first reactor, the conversion at a 0.1 is x1. For this case, x1 is equal to 0.4. After passing the second reactor, conversion is x2. For this case, x2 is equal to 0.8. Okay, so this one is the simplest combination of only two PFR connected in series. So what's the formula for this system? If we consider the total reactor, I mean the seriously connected reactors, the conversion at a final point, the conversion is x2, right? So integral from 0 to x2. This is the target for integral dx. Okay, so this formula is for the combination of two reactors. It can be separated into two terms. The first one, this one is for the first reactor. Okay, for the first reactor, at the beginning, the conversion is 0. After passing the first reactor, conversion is X1. Okay, so how about the second one? For the second reactor, the conversion is from X1 to X2. Okay? And also remember, this term is still FA0, still FA0, not FA1 or FA2, still FA0 because the definition of conversion, right? Remember the definition for conversion is based on the molar flow rate at the beginning, FA0. Okay, because the definition. So this one, the molar flow rate is still FA0. Also, you can just check the mathematics formula. This one, the range is from 0 to X2. So you can divide it into two sections, right? Two intervals. So you can do the integral at this range or do it twice. So this one, the total can be separated into first and the second reactors. How about the figure? For some reaction, the curve may be like this, okay? If X1 located here, X2 here, X1 and X2, okay? So for the volume of first reactor, do you remember? For the first reactor, this area is the same as the volume of reactor 1, right? What is the total volume? If we only talk about conversion equal to X2, I mean you combine two PFR in series. The final conversion is X2. What is the volume? The volume is in the integrated area of this curve, right? Under this curve. So the blue circle is the same for the total volume of two reactors. So how about the volume for second reactor? This one is the volume for second reactor. This one is the volume for the first reactor. So you can compare this figure with this formula, okay? Then you will know, use only one reactor or two reactors in series, the volume is the same. For PFR, connecting several PFR in series cannot reduce the volume. So use one PFR or a lot of PFR in series, the total volume is the same. But for the previous example, if for CSTR, connecting CSTR in series can reduce the value, right? CSTR is okay. But PFR, seriously connection, cannot reduce the value. Let's see one example you will know better about the PFR in series. Slide 35. Sizing PFR in series. So again, we use the same data. We use this data for several examples, right? So we use the data in table 223 and the figure 222. I think at least I put a table in this slide. So the same table use data to calculate reactor values. So this example, we have to find the V1 and the V2. Okay, V1 and the V2 for PFR in series. Okay, and the intermediate conversion, X1 is equal to 30%. Final conversion, X2 is equal to 80%. The entering molar flow rate, FA0, is 0.4 mole per second. Very familiar data. And also the table shown in your handout. Okay, so let's use the, it is a PFR, right? PFR. We don't have the equation. We only have 7. We only have 7 points in table 223, right? We only have 7 points. We don't have equations, so you have to use 5 points or 3 points formula. Let me use. Also, the 3-point formula is called Simpson. I don't remember I have tell you this one or not. Simpson's rule is the 3-point formula from x0 to s2, integral of f of x. Okay, so this one you can use only 3 points. The coefficient is 1, 4, 1. I think previously maybe I put a F0, F1, and F2. I think. The same, okay? The same thing. What is delta x? Maybe I have h previously, right? Delta x is equal to h. Okay, so let's find the V1 first. Find the V1. So, V1, what is x0? X0 is 0. For V1, the final conversion, for V1, reactor 1, final conversion is 0.4, not a 0.8. V1, okay, V1, 0.4. F of x, always this one. For this case, we need a 3 point, right? 3 point. The starting point is 0. The final point is 0.4. So the middle point is 0.2, right? So first, 0.4. Middle point is 0.2. Interval 0.2. Okay, so delta x is 0.2. F of x0. F of x0, you have to check the table at x equal to 0. F of x is equal to 0.89. How about f of x1? Check the point. X is equal to 0.2. F of x is equal to 1.33. The last one, x equal to 0.4. F of x is 2.05. Okay, Simpson rule is much easier. Don't forget the unit. Unit is important. It is V1. So similarly, let's find a V2. Find a V2. Maybe you can find a middle point and the interval first. So for V2, the starting point, the conversion is 0.4. Final 0.8. Okay, for x2. Middle 0.6. Interval 0.2. So again, V2. F of 0.4, right? The first point, 2.05. Second one, x equal to 0.6. F of x is equal to 3. Okay. The last one, x equal to 0.8. F of x is equal to 8. Okay, so that's V1 and V2. Finally, let's compare the total volume for PFR in series. So how about V1 and the V2, the total volume? you can check this volume. I think you are familiar with this answer, right? This answer is the same as equation example 223. Okay, example 223. Example 223, we talk about sizing a PFR, a single PFR. So at example 223, the volume is the same. It's the same, okay? So it is useless to connect PFR in series. Useless, okay. The total volume is the same. Okay, we have talked about CSTR in series and the PFR in series. The last part, we can combine PFR and the CSTR in series. This is the last section in chapter 2, the last one. Okay, so please go to slide 37. Combinations of CSTR and the PFR in series. For example, okay, 3 reactors, CSTR, and the PFR. Again, let's write down the molar flow rate. Okay, so at the beginning, the molar flow rate, FA0. After passing the first reactor, molar flow rate is FA1. After passing the second reactor, the molar flow rate is FA2. So after passing the third reactor, molar flow rate is FA3. Okay, so along with molar flow rate, we have conversion X1, X2, and X3. Okay, so let's talk about this combination. Okay, so for reactor 1, so I will directly write down the formula. Okay, I will not start from a general Moore balance equation. If you want to derive the formula, you can check the formula before. I have derived the formula before. Okay, so for reactor 1, CSTR. So the volume is V1, okay? It is equal to RE1, okay? The reaction rate may be different. So RA1, X1. Reactor 2 is still CSTR. V2, FA0 over reaction rate 2. X2 minus X1. Okay, so as I told you before, if you want to have the same font, maybe you can write down like this, right? X1, X0, X0. At the beginning, conversion is equal to 0. So the same form, you can write down like this or delete the 0 term. It is okay. Reactor 3. The volume is equal to V3. Actually, the formula is similar, but for PFR, we have to use integral, right? Integral from S2 to X3. F of X is the same. FA0 over minus RA. This formula is not new. It's not the new ones. We only use the formulas we have learned, right? And do different combination. For the figure, again, the y-axis, FA0 over minus RA reaction rate unit. The x-axis is conversion. 0. Okay? So for the same curve like this, x1, x2, x3. Okay, assume x1, x2, x3. How about the value? How to find the area corresponding to the volume of a reactor? So first one and the second one are CSTR, right? So for CSTR, you have to find this point, have a rectangle. Yeah. This one. Okay, V1. The second reactor is also CSTR, so find this point. This one, V2. Last one is PFR, the integral area under the curve. Okay. So again, you can use two methods. You can use formula, or you can calculate the area in the curve. Any question? We have another example, right? Another example for the series connection of reactors. The combination of CSTR and the PFR. Okay, if you are okay, let's go to example 227, slide 38. An adiabatic liquid phase isomerization. But isomerization is not important for this class, right? So maybe this one is like this one. Not important. Okay, calculate the volume of each of reactors. Let me first draw the scheme. Okay, so this reactor, first one is CSTR, second one is PFR. You have the figure, right? The last one is again CSTR. 这样比较好看。Okay, so 3 reactors connected in series. The sequence is different as this one, different, okay? So you have to find a V1, V2, and the V3. Again, FA0, FA1, FA2, FA3. Okay, conversion X1, X2, X3. You can have a point. Okay, so let's talk about this system. X1 is equal to, actually there are number. X1 is equal to 0.2. X2 is equal to 0.6. Okay, X3 is equal to 0.65. The data, the information is in the figure. Okay, you can find the information. Conversion, X1, X2, X3. Also, we have FA0. From the sentence, entering molar flow rate is 50 kmol per hour. So FA0, okay. We can just put the information here. FA0 is equal to 50 kmol per hour. Okay, so first, there is a table, right? We need a table. We need a data. We need a data to calculate a value. So how about the table? The table shows 5 points. And the table gives you X and the reaction rate. But do you remember what is the important parameter? FA0 over reaction rate, right? So you have these two. You have this one. Also, you have this one, right? You have to calculate this one. You have to calculate this one. So at the beginning, let's finish this new table. So originally, in the example, we have 1, 2, 3, 4, 5. Okay, we have 5 points. And also at this point, we got a reaction rate. Okay. Let me put a unit, sorry. Unit is important. So please put a unit. It will be easier for you. Okay, unit. So we don't have to do the conversion of unit, right? Because the unit for reaction rate, kmol per hour is the same as molar flow rate. So it is okay, you don't have to convert unit. So this one is, okay, right? 50. Reaction rate, 39. So actually the answer so in the table, you have to give me the yellow numbers, okay? I just put a calculation for you only. You don't have to write the list. You have to give me this. Let's continue next class, okay? Take a rest.喂，上课哦。So let's use the table. The table with FA0 over reaction rate. So V1 is for CSTR, right? V1. The formula for V1 is X1 is equal to 0.2, right? So FA0 over minus RA1 is 0.94. This one. Wait.喂，我有声音吗？变小了欸。喂，好了，就这样了，没关系啊。So x1 is equal to 喂，好 ，x1 is equal to 0.2. FA0 over minus RA. Okay, this is V1. The second reactor is PFR. So you have to use the Simpson's rule, 3 point. Okay, so for second one, V2 use integral from 0.2 to 0.6, right? X1 is equal to 0.2. X2 is equal to 0.6. I want to directly write down the 3-point formula, okay? So for this 3-point formula, this is the interval from 0.2 to 0.6. Okay, the middle point is 0.4. The interval 0.2. So first one is the f of x at 0.2, right? At 0.2. Second one, coefficient is 4. F of x at 0.4, so this one. The last one, f of x at 0.6. Okay? The third reactor is CSTR. So we use the very similar formula like this, but replace x1 by x3 minus x2. It's not difficult, right? Only two kind of reactors, CSTR and the PFR. So only two kind of formula. One is the simple calculation. The other one is to use integral. So be careful of the FA0 over minus RA you used. This one. Choose the correct one from the table. And from the table, remember to calculate FA0 over reaction rate. So originally, maybe this information is not shown in the table. You have to calculate FA0 over minus RA. It is a very important term for calculating the volume of reactors. So let's draw the area, okay? Let's find the area in the curve corresponding to the volume. The curve is new. For this example, we use a new table, right? New data. So the curve is not like the curve in previous examples. We have a new curve. Okay, let's draw the curve. The closer the better, okay? The closer the better. Okay, so it's like this. It's like this. So previously, we only have the experience on this kind of curve, right? For previous examples, we only use this kind of curve. So let's see if the data, if the information is different. But you can use the same way to find the area corresponding to the volume. So there are three reactors. X1, what is X1? X1 is equal to 0.2, right? X1. X2, X3. Okay, so X1 is V1. The first reactor is CSTR. Okay, CSTR. So how to find the volume for CSTR? X1 here. X1 here. So okay, rectangle. Now the integral area. This one, only this one. This area V1. Okay. Second reactor is PFR. So PFR, the area, the integral area, right, under the curve. So from point 2 to 0.6, from X1 to X2, from X1 to X2. You got this one. Okay, this is the The area is the same as the volume of reactor 2, V2. Again, the last reactor CSTR again. So V3. Okay, from this figure, I have one question. How to reduce the total area by replacing only one reactor? Okay, you can see this figure. The total area of this system, you sum up this one, and this one, right? The area, these three areas is the total area. So how to reduce the total volume? You can change CSTR into PFR or change this one into this one. You have these choices. So do you know the answer? You can see here, this part. Because the curve is a little bit different, as we talked about before. So maybe you find that this area is smaller, right? This area is smaller than this one, right? Okay, the difference, this part, the difference on the volume is this area. So you can, the answer, you can replace reactor 3 using PFR. Now you can reduce the volume. So depend on the curve, different connection, different sequence of CSTR and the PFR you have to use to find the smallest volume. If your purpose is to is to establish a reactor with smallest volume, you have to observe. It is easy to just observe this figure. It is easy, right? Because you can find this part. So you know, if you use PFR, the area is like this, under the curve. But you use CSTR, the area is like a rectangle. Okay. Okay, let's go to slide 41. Some further definitions. The last part. Let me introduce you two parameters, space-time and space velocity. First, what is space-time? They are another name for space-time, like holding time or mean residence time. That means how long your reactor or your product stay in the reactor, how long. So it is time. And we talk about the volume. So the definition for space-time is equal to volume over volumetric flow rate. Okay, so volume over volumetric flow rate, the unit is for time. For example, okay. So this time is also for, I have listed two sentences under the space, under the blank region. Okay, first, the time to process one volume of reactor. The time to process one volume of reactor. The other meaning, the time for the reactant to enter or exit the reactor completely. But I think these two descriptions are very similar. So by using the space-time, you can estimate how long the process will take. You will know how long you should wait for finish this process. So for example, if a reactor with volume 0.2 cubic meter, the molar flow volumetric flow rate is 0.01 cubic meter per second. The space-time, it is easy, right? What is the space-time? So the time to process one volume of reactor is 20 seconds. Okay. So for 1 minute, you can process 3 times of the volume of reactor. So relating to the space-time, we have space velocity, or you can call it SV. However, it is similar to velocity, but it is not velocity. You can see the unit. SV is the inverse of space-time. So it is V0 over V, inverse of space-time. So you can find the unit is not a velocity. The unit is time over 1 over time, right? The unit. But the unit for normal velocity is length over time, right? Length over time, like meter per second. The normal velocity, the unit is length over time, like meter over second. But SV, the unit is only 1 over time. So a little bit different. It is the inverse of space-time. So this one and the latter one. So you have space-time and you have space velocity. Okay, so that's the last example. The easy one. Okay, so you can find the definition is very easy, right? You have volumetric flow rate, then you can get a space-time and a space velocity. The example is also very easy. The example is to calculate space-time and the space velocity for the reactors in example 222 and 223. Okay, so in this example, it used the same data in previous examples. So let me directly get information from previous examples for you, okay? So as you know, in the definition, you have to find volume and the volumetric flow rate. Okay, so there are 4 answers, right? For example 222, we got a space-time and a space velocity. For example 223, we got a space-time and a space velocity as well. So the unit is not required to be hour. It is okay for you. But you have to check if the unit is required by the question. You have to check the unit. So this time I directly use the volume we calculated before, right? But if you are taking an exam, you cannot find a volume in your handout. You have to calculate the volume by yourself. So you may find this example is easy. That is because we use the volume we have calculated. Okay, if you want to solve the space-time and the space velocity at the very beginning, you have to calculate volume by yourself first. Okay, then use these simple definition, simple formulas to find the 2 parameters. Okay, so that's all for chapter 2. There are some summaries listed at the last several slides. You can check it by yourself. Okay, I don't want to repeat again. I suggest you to list the simpleton rule at slide 46. The last slide I have listed. I think I have listed the numerical integration method, the 5-point method, right? 5-point formula. If you want to review by using this summary, you can also put a simpleton 3-point formula at this slide. It will help you to memorize. Okay, you have chapter 3, right? So let's go to chapter 3. So in chapter 3, the content is still similar to chapter 1 and chapter 2. I mean, we will still talk about batch reactor, CSTR, and PFR. Still, but what's new? In this chapter, you can see slide 2, what we can learn from this chapter. In this chapter, the main purpose is to, is to write a function of reaction rate using conversion. That is the purpose. So how to achieve this goal? First, so actually there are 2 parts in this chapter. At the first part, we will talk about rate law. Okay, so what is rate law? Rate law is to write the reaction rate using concentration. So in the first part, we develop reaction rate using concentration. There could be several concentrations, right? So it is the first part, rate law, to write down the function of reaction rate using concentrations. But this one is not this one, right? This one is not this one. How to achieve this goal? So at the second part, we use stoichiometry. So what is stoichiometry? Stoichiometry is to find the concentration as a function of conversion. So maybe CA concentration, certain concentration as a function of conversion. Okay, so actually this one is this one, right? So if you combine the rate law and the stoichiometry, if you combine rate law and the stoichiometry, finally you can write down the reaction rate as a function of conversion. That is the purpose. Okay, so do you know what is the purpose? Why we have to write down the formula, the function of reaction rate by using conversion? Because you have seen this for many times, right? For many times. So in chapter 2, how to solve this one? Use 3-point or 5-point formula, right? So you have to get several data like 7-point or 4-point or 5-point. So you want the table. So previously we solved this one using the table. Okay, but if you can write the reaction rate as a function of x, then you can do the integral directly. You don't have to use approximation. You don't have to use a 3-point or 5-point formula to find a similar result. You can find an accurate answer by using this one. Okay, so that is the purpose in chapter 3. Find this one. Okay, so there are more things I want to tell you for stoichiometry. For this part, if you remember, for batch reactor, we talk about moles and moles. For flow reactor, like flow reactor, PFR or CSTR, we talk about molar flow rate, right? FA. And what is the relation between concentration and mole? The relation between concentration and the moles or molar flow rate related to the volume, right? Volume. So concentration is equal to moles over volume, or molar flow rate over volumetric flow rate. Remember, right? So for this one, you don't have to directly write down concentration as a function of conversion. You don't have to directly find this one. You can try to find these four related to X. Okay, so let's go to the part one rate laws. Some basic definitions. Let me introduce a little bit about the basic definition. Okay, but for most of these definitions, I think you are familiar with, like homogeneous and heterogeneous reaction. The difference between homogeneous and heterogeneous is the phases, is the number of phases. So for only one phase, that is homogeneous. For more than two phases, that is heterogeneous reaction. Okay. The second class is irreversible and reversible reaction. Okay. So irreversible means the reaction only proceeds in one direction. The reversible reaction means the reaction proceeds in either direction. Okay, so following molecularity. Molecularity means the number of moles and number of particles. Yeah, number of atoms or ion or molecules. So the last term is related to the molecularity. So you put something before molecularity, like uni or bi or ter. That means one or two or three atoms in one reaction state. Okay, so the last two terms are similar, just have some letters before molecularity to describe how many atoms used in one reaction. Okay, so let's go to slide 5. Relative rates of reaction. So for a very simple reaction, so for a simple chemical reaction, AA and BB becomes CC and DD. So commonly, the coefficient for A, we will divide the coefficient A in the whole chemical reaction. So the A is always limiting reactant. So put a coefficient equal to 1 for the limiting reactant. It could be easier for you. So what's the relation between reaction rate of A and the reaction rate of B? the reaction rate is proportional to the coefficient, right? And the reactant and the product has different sign. So for reactant, you have to put a minus sign before. So minus RA, because A is the reactant. A is the reactant, so minus RA. C is the product, so RC. The relation between RA and RC is C and A, the coefficient of this species. Okay, so you can know the relationship between the rates can be expressed from the stoichiometry of the reaction. Therefore, for AA, BB become CC and DD, you can write down this relation. So you just put a coefficient here, the corresponding coefficient, and put a minus sign for the reactant, positive for product. So that's the relation between these four species. Okay, so let me finish the last example. Okay, slide 6. A real example. Okay, so again, you see this chemical reaction. Reactant, minus sign. Product, positive sign. And put a coefficient under. Then what is the relation between them? If the nitrogen dioxide, NO2, if NO2 is formed with reaction rate 4 mole per cubic meter per second, okay, you find the reaction rate is -4 or -2. That means Because you want to find the formation rate, but the answer is minus. That means this species are not formed, right? It is consumed. So the minus sign means disappearance, not appear. Okay, let's stop here.